Okay, welcome and thanks for joining in person, and thanks for joining in via video stream. So I'd like to welcome Joosep, who will be talking about his machine learning experience, large-scale machine learning experience, and I think you are willing to take questions.
Sure, at any time throughout the presentation. So just interrupt me if you feel like something was unclear or you would like to know more about something, because I could not fit, of course, everything into the slides. So just ask me to expand on something if you want to.
Okay, thank you, and please.
Okay, so thanks for the invitation to speak at this this course. My name is Joosep. I'm a staff scientist at the National Institute of Chemical Physics and Biophysics. I'm working since 9 years, basically with the CERN LHC project, and one of the big focuses there is machine learning. So then this is a good fit, I think, for this course. So let's see if I can move the slides. Yes. So okay, just a few caveats. So everything that I'm speaking here is in personal capacity. I'm not representing the experiment. I'm not representing my employer. This is really just kind of views from the trenches, experiences that I've collected over the years. And I'm not going to be talking about one particular favorite model of mine or anything like that. This is mostly a summary from the high level of various aspects of how machine learning is used in high energy physics. So it's not really like a deep dive into a single paper, but rather it's a kind of bigger summary of things. And if you're interested in sort of a review of what are we doing with machine learning in high energy physics, then there is this great GitHub repository where people are collecting sort of living review of all the papers that are coming out as they come out. So this is a very good up-to-date place to see what's being done in our field. And if you want to learn more about basically the technicalities of machine learning, especially from a high energy physics angle, then CERN has a lot of great open lectures, free lectures that have been recorded, and you can watch at any time. So there are ones, for example, by Michael Kagan, which I've linked here. So if you go to the CERN library webpage, you can search for machine learning lectures there, and you'll find lots of great resources. So just to give a bit of context, what is the LHC? What are the projects there? What are we doing? So this is an aerial view of Geneva. Here is Lake Geneva, the Alps in the background, Mont Blanc. And the LHC is a 27-kilometer tunnel that's under the ground. And we have a particle accelerator in that tunnel. And we have several experiments on the particle accelerator, which basically measure what sort of particles are produced in proton-proton collisions. So I work at the CMS experiment, which is here in the French countryside. The CERN itself is a kind of scientific campus that's located here on the border of Switzerland and France. And what's currently ongoing at the LHC? So this is a time schedule as of this year. Currently, we are here in the middle of, or towards the end of 2021. And basically, you see here in light green is a so-called proton physics period. So this means that's the time when we actually collide particles, we take data, and we kind of produce results. So we have now been in shutdown, during which the machine has been undergoing upgrades, improvements, and now in the next 2 or 3 years, we will be taking data again. So actually, it's a very exciting time in particle physics because we are about to take data again. We have been doing a lot of improvements, a lot of upgrades, and then we kind of switch to our main mode of operation again. And this will go on for 3 years. Then we will have another shutdown for a couple of years, during which we will do yet more upgrades. And then basically we'll start the so-called high luminosity run, which will last for something like 10 years, and during which we will basically collect a huge data set from which we want to basically extract everything that the LHC is capable of measuring. So this will be sort of our legacy to the scientific community. So everybody is now working on essentially algorithms for this data taking era, for this high luminosity era, where the data rates will be so high that we need to really radically change how we are analyzing the data. And what are the questions that we're trying to answer with the LHC, or what's the big idea there? So here is one of those questions: how do particles acquire mass? So you may be familiar with fundamental particles, electrons, protons, so on. But the basic question is, there is so far only one consistent way to give those particles mass, and this is the Higgs mechanism, which you may have heard about kind of in newspaper or so. And this was a sort of idea proposed maybe in the 60s. And we have been able to actually experimentally confirm that this mechanism indeed works as proposed. So this we achieved in 2012 when the Higgs boson was discovered, so-called Higgs dependence day. So here you see the famous PR plot of the Higgs diphoton mass. So the Higgs decays immediately to different particles, for example, photons. And then you can measure those photons and you can kind of see, do you observe a resonance peak in the photon spectrum? And here, this is kind of the PR plot that we can make from this. You do observe a little peak away from a falling background, and that is the Higgs boson. And this is actually so far the first and only observed particle that has no spin. That's a fundamental particle. So this is really something new as well. You know, it was predicted, but also it's a totally new type of particle that so far was not measured. So this is a sort of new window into the world of fundamental physics. So this was in 2012. Then in 2019, basically at the end of the previous data taking period, we could already measure how strongly does the Higgs boson sort of couple to other particles. So here it's listed different types of particles that the Higgs boson can couple to: muons, tau particles, B quarks, WZ bosons, the top quark. And so horizontal axis is the mass of those particles, and you see this spans like 3 orders of magnitude. And on the vertical axis is basically coupling strength. So the higher this number, the stronger the Higgs boson couples to the particle, which means also the higher the mass of the particle. So this is essentially the mechanism of mass generation. The stronger the Higgs boson couples to it, the higher should be the mass. So we want to experimentally verify this. And we have been able to do this basically in 7 years since discovering the particle, then doing statistical measurements on this, doing really detailed checks. And we observe basically that the mechanism works. It does what it's advertised. It's really giving the particles the mass. So this was the progress of 7 years. And then what we want to do next by the end of the high luminosity period is to essentially measure how strongly does the Higgs boson interact with itself. So this is one of the fundamental unknown quantities in nature. What is the strength of the self-interaction? Because that essentially determines what is the long-term future of essentially our universe. Because the way the Higgs mechanism works is that we are currently in a sort of stable state, but this may or may not be the final stable state of the universe. So if we can measure how strongly the Higgs interacts with itself, we can determine if this state where we're currently in is metastable or is really the lowest point of the energy spectrum. So you can see this in this little figure here, that we are currently in this point here, and we don't know really what is the shape of the Higgs potential as we go away from the equilibrium. So basically the main goal of the LHC program is to answer these kinds of fundamental questions about the universe, like what are the mechanisms by which all the particles interact and how does this all work? So this is the big project. And how far have we gotten, or sort of what's the current state of the art? This is a plot from my experiment, where essentially on the vertical axis we have the cross section, or in other words, the sort of probability of certain processes. And on the horizontal axis, there is a lot of different processes. So like producing W bosons, Z bosons, all different kinds of particles that we have in fundamental physics. And there are 2 kinds of dots on this plot. One are measurements, so in these colorful squares. So 7 at different energies in the experiment, we have done measurements of different processes, and then in gray we have the predictions from the standard model of physics. So essentially you can do very detailed calculations for each of these processes and see what should be the probability of this process, and then measure it. And we have basically done this for all of these processes, and to a large extent we see that the measurements kind of reproduce very well what is predicted by theory across many different orders of magnitude. And this is basically a big success of fundamental physics, that we can predict very accurately so many different kinds of processes, and this also matches up with measurement. So none of these processes we can see by eye. We really have to do a very sort of detailed data analysis for each of those. So this means we have a very predictive model, which is able to explain a lot of things in particle physics. We can also check this. So then the question is, where do we go forward from here, right? So we can use then this very, very good model that we have as a starting point to check for any deviations of the data from this model. So this is kind of the program going forward. And this is actually something that's unique in particle physics, and which also gives us a handle to machine learning, because in typical machine learning problems, you do not have an underlying theory which tells you how things should be. Like for real life, real data cases, like, I don't know, classifying images, you do not have an underlying mathematical theory. What should the image be like? Here we have a mathematical theory, very predictive, as you can see from this plot. And we have also big questions to answer from this data. So essentially, like, we have to look at much finer deviations than in perhaps other fields. So we have a good model. We have a lot of data. So machine learning is actually very, very interesting here. So a few words about these experiments then. Basically, we have two general purpose detectors at the LHC, the CMS experiment, which I'm a part of. So here you can see kind of a cross section of the experiment when the experiment is opened. So this is during operate procedures. And for scale, I guess you can see like a little wheel of some kind of mechanical contraption here. So this is huge. This is like 10, 20 meters across. And here is the Atlas experiment. Basically, it's a kind of competitor or cross-check to each other. And they use slightly different technologies for certain detection, but the idea is more or less to measure the same processes, just to cross-check each other. So then we can go into one of these detectors, the CMS detector. We call it sometimes the cylindrical onion because it's essentially cylinder shaped and it has different layers like an onion. Each layer has a different purpose to detect different kinds of particles. So here in this orange, we have the beam pipe, and essentially the proton-proton beam is focused here in the center where the collision happens. And then we have different detector layers. For example, here in the very, very center, we have the silicon trackers, which are essentially like 60 megapixel camera, which takes images 40 million times per second. So it's a three-dimensional camera essentially. And it basically takes images like a point cloud. So then from this point cloud, we have to reconstruct what were the particles that made this point cloud. You can immediately see that this is a sort of huge data problem, needs to run extremely fast. And there is sort of a lot to disentangle there because everything can overlap in principle. So it's really complicated to reconstruct. Then going from inside out, the next layer we have is the electromagnetic calorimeter. So this is essentially a fine-grained crystal, which measures the energy of electromagnetically interacting particles like photons and electrons through these so-called electromagnetic showers. Then the next layer is the hadronic calorimeter, or HCal, which is essentially brass, which according to the legend, the brass was previously Russian World War II cannons, which were melted and then used for this part of the detector. Then comes the superconducting solenoid, which has magnetic field 8 Tesla, which as far as I know is the largest magnetic field in this scale of an object on the Earth, basically. And just to give some context, the current required for this field is 18 kiloamps. So it's a pretty unique thing. And then, so the idea of this magnetic field is that it creates a very strong sort of magnetic field inside the detector. So all the charged particles, they will have to curve. And then you can use the measurement of the curvature to determine what was the charge of the particles, like to distinguish plus from minus, for example. And then at the very outside, we have the muon chambers, which essentially measure these particles which penetrate everything else, and they just take up sort of the rest of the measurement. So you see we have a lot of different layers. Every layer has a different purpose, different granularity. So the idea is that for the data reconstruction, we have to actually put all of those together somehow. So let's look in a bit more stylized way, this particle detection problem. Yeah.
Excuse me, the thing that you said before about the 3D image detection, like when you said that it's a linear problem, then you have to like make multiple shoots to get like the volume information. Like it's somehow the same idea of a gravimetry, like that you detect the gravity from many different points and then you like make like a huge linear system of
right. So I guess what I meant was that you know, if you have a single particle flying through some kind of a grid and leaving little dots there, it's very easy to reconstruct what it was, right? You just connect up the dots and that's it. But if you have 100,000 particles, then there's dots all over the place and you don't know what's what. So you kind of have to, it's like a huge combinatorics problem, essentially, that if you want to reconstruct what were the particles from the collision, you have to disentangle all of those at the same time, effectively. So I have another picture about this particular problem. It's actually one of the hardest parts of the reconstruction is this tracking, and that, yeah, a lot of attention is focused on this at the moment. Any other questions? At the moment, I see there is something on the Zoom chat. I'm not really following it myself, but
I'm following it. Yeah.
Okay.
Yeah.
All right. Any other questions so far? So if we look a bit more into what's going on in the particle detection, so here we look at the transverse slice of the detector. So the beam is coming in and out of the screen. The collision happens here at the center, and we can produce different types of particles. For example, if we produce an electron here in the red line, then it will travel in a curved line because of, or a curved trajectory because of the magnetic field. It will leave some hits in the silicon tracker, which we can use to reconstruct the trajectory. And it will leave a kind of energy deposit or cluster in the electromagnetic calorimeter. And it will penetrate no further because it will basically interact or leave all its energy there. If we have a different type of particle, for example, a neutron, shown here with the green dashed line, it will not leave any signal in the silicon tracker, so in this central camera. It will also not leave any signal in the electromagnetic calorimeter, but it will leave a huge energy deposit in this brass scintillating hadronic calorimeter, and so on and so forth. So you see different types of particles really leave different types of signals, and it's not like this particle leaves just like one bit that we just see that there was a particle and that's it. Usually the signal is very complicated, like a cluster of different kinds of things which you have to put together in the presence of other clusters. So it's always like an overlapping problem, essentially. So then we have these reconstruction algorithms, which do all this work at the detector. And so starting from inside out, kind of in a very simplified way. So first we have the charged particle tracking, which you asked about. So essentially here you see a little image of the detector with a collision happening in the middle. And you have something like 10K charged particle tracks for each collision. So 10,000 and 100 million of those per event, or per second, sorry. And so you can imagine each of those 10K leaves a bunch of different dots you see at the same time. So then you have to reconstruct those 10,000 tracks kind of from the same huge point cloud. And that's, yeah, very challenging because of the sort of overlap problem there. But we are able to do this very well already, you know, since 10 years, even basically without machine learning, using traditional algorithms like Kalman filters and you know, you first reconstruct the simple stuff, then you remove it, then you do another iteration, you remove it, and so on and so forth. So there are solutions already out there that work. The problem is, essentially, it's computationally quite challenging. So the more particles that you have, the more expensive it gets by kind of sort of almost quadratic way. So this, if you go into the high luminosity period where you have a lot of interactions per event, this gets extremely computationally expensive. And the other problem is that, of course, every additional bit of physics information you can get out from this is going to give you a huge boost in the analysis later on. So if you can do a bit better reconstruction, this can save essentially a lot of data taking time. So we want to have algorithms that are as good as possible from the physics point of view as well. So, and if you write some kind of a, let's say, Kalman filter by hand, you can tune it, but it will never be optimal in some sense. Like you always have to make some compromises when you write down these algorithms. So when you run something, you want to be fairly sure that it's as good as you can get. So their machine learning also offers an interesting possibility. So then moving on from tracking, if we have a particle that is detected by the calorimeters. For example, let's take an electron. And as I mentioned, the electron is charged and flying in a magnetic field. So it basically flies in a curved trajectory because of the usual Lorentz force. So this means that every once in a while, it has to emit photons to make up for the momentum difference. So the electron flies, emits photons every once in a while. So it kind of makes like a little radiation pattern. And this means that essentially, if you look in the calorimeter for an electron, you see first a big energy loss photon cluster in, from the first sort of energy loss, and then it gets smaller and smaller and smaller until finally the electron itself makes it to the calorimeter. So you have like a little stream of calorimeter clusters. So then the idea is you want to kind of link them together, because you have to treat them all together if you want to reconstruct the original energy of the electron. So you see, you come into a kind of linking or clustering problem again, that you have many independent little signals and you want to know which of those go together. So then you can look at the reconstruction as a sort of like outside-in problem, that here you have the detector, again, a transverse slice. You have different layers. So here we have the most granular hadronic layer outside, with the electromagnetic layer in the middle, and the tracking here in the very center. And you have different types of particles flying in different directions. And you kind of want to correlate the signals from this part with the signals from this part, with the signals from the center, and make up sort of the best representation of what were the particles that actually were produced. And again, we have traditional algorithms to do this. So kind of they really start from the things that are easy to understand. For example, here you see this very distinct little line here, and you can say there is nothing else close to it. So why don't I just take this line? I'm going to take whatever track is matching up with that line. I'm just going to remove those. And then, you can kind of do this iteratively. But as I mentioned, again, this has limitations with the physics performance and also computational performance. So the goal is to kind of develop algorithms that would essentially look at the whole picture at once, and then reconstruct the most optimal set of particles that you can from this, using, for example, machine learning. And then the idea is that you essentially reconstruct the particle candidates, and based on the physical properties and the distributions of those particle candidates, you can say something about physics. So for example, here on the top right, we have again the diphoton invariant mass plot. So you look at all the events where you had exactly 2 photons, and you add up the energies of those photons. You get this so-called mass variable. And if there was a resonance particle that produced those photons, you would have a little bump in the spectrum, which you can interpret then as the Higgs. So this is kind of crucial for actually discovering the Higgs. The other thing you can do is you can sort of measure all the hadronic energy in the event, and you can get this so-called jet spectrum, where essentially you're measuring energies over many different orders of magnitude and checking how well does what you measure match up with what's predicted by the quantum chromodynamics theory that's underlying this whole process. And here again, we can see sort of very good agreement, first of all, and secondly, that the algorithms kind of work. So then the question is to do better than this, essentially. Any questions so far? Something that I could explain a bit more? I mean, it's just kind of really snapshots and cartoons. It's not really a detailed overview, but something that you would be more interested in.
Like the data sets in which the algorithm learns, it's like the previous experiments that you had that you could like as a sample.
Very good question. So what are our data sets? We always have a very good simulation, as I mentioned, basically because the theory is already so good that for many cases, even for the future experiments, we can do a really accurate simulation of what we expect the signal to look like. And that really gives us a big handle into also using machine learning, because then we have a basically supervised data set that is as big as we want almost. So that's one thing. But then the other thing is, of course, simulation is never real life, right? And you want to kind of, whatever algorithm you develop, you first want to check that it would work on the previous data. And then you want to also do tests on the new data that it does work. So you have certain processes where you can calibrate your measurement, like sort of standard candles, where you know what happens. And you use this to essentially measure your response, and you can extrapolate this then to some unknown region.
Sorry, as understood, this is reinforcement learning.
mostly we use supervised learning because we have like exactly the ground truth. Because in simulation, we know what happened, we put it in there ourselves. So we essentially have classification and regression problems for the most part. Reinforcement learning, we haven't really looked into that much so far, at least not in production, more for like really R&D stuff. Okay, so then going a bit more into a particular problem that we're trying to address with machine learning algorithms at the LHC is identification of these so-called jets. So I have to explain a little bit what are these jets. So basically, when two protons collide, they produce high energy particles like quarks and gluons. But these quarks and gluons, they have a color charge, so they cannot live by themselves. They very quickly essentially neutralize themselves. They produce like a spray of particles that is then detected in the detector. So you see here a quark being produced, and then very quickly it generates friends for itself, other quarks and gluons. So it evolves down to a lower energy. Those produce then stable particles, and those stable particles are detected in different parts of the detector as a kind of image, if you will. So basically, the jet is a kind of an emergent phenomenon where you start from the femtometer scale and you evolve down to a meter scale because the detector is like macroscopic, it's human size. So you go like 15 orders of magnitude in a fraction of a nanosecond essentially. But based on the structure of this image here, you can infer stuff about what was this particle here. So we actually want to distinguish, for example, was this jet produced by a quark, like blue particle, or gluon, different kind of particle? And this can give us information about what happened in the collision. So just to give an example, what are the different kinds of jets that we can produce? So one is already, as I mentioned, is quark and gluon jets. So quarks produce narrow jets and gluons produce wide jets because of how they interact differently with quantum chromodynamics. So this is a kind of simple rule of thumb, but then in the end, you cannot encode this in like one variable. So essentially machine learning turns out to be the best tool to distinguish one jet from the other. The other case you have is if you produce very rare heavy quarks, like top quarks, then those, when they decay, they produce like a special prong pattern. So the jets would have like a substructure where you can identify like 3 different little subjets in the jet. So this becomes again sort of, you could say, image recognition problem in some sense. Or you have different kinds of jets which are produced from so-called B quarks or B hadrons, where essentially the defining property is that the jet has like a little internal structure where the charged particles in the jet don't start from the beginning of the jet, but they start in the middle. So if you extrapolate the trajectories of those charged particles, you see they don't go back to the starting point essentially. So the idea here is that basically there's lots of different processes which make jets. And if we can determine what was the origin of the jet, that's really helpful for us. But there is never like one single thing that you can use to distinguish different types of jets. So it really becomes a machine learning problem. So here's an example from the CMS experiment. Here is one jet in simulation. And basically you see a bunch of charged particles here in the curved trajectories, a bunch of neutral particles here in the dashed lines, and then different kinds of colorimeter deposits here in the different colors of ugly gray or ugly green. And the idea is you just see this in your detectors. Now your question is, what made it? Was it the B jet? Was it the top quark? Was it quark gluon? I don't know, right? So, and you want to do this for hundreds of millions of cases. So we want to answer this question, what is the originating particle of the jet? So what can we do? As I mentioned, and as you already also asked, basically the question is about the data sets. And since the standard model works really, really well for certain kinds of predictions, we can basically run this machinery and produce like simulated examples. What would jets of different type look like in the detector? So we make proton-proton collisions, we produce different kinds of jets, and essentially we can generate fake data sets like this one here. So here we have the particles in, so each image is one jet, and we have like kind of the X and Y plane of where the jet hits the detector. And each little dot here is one constituent particle of the jet. The size of the dot would be the energy and so on. So, and blue and red are different types of jets. And you see that the patterns are kind of always different. And in principle, they should also be different between blue and red. So red is actually these top jets, which you see have like three three main clusters, if you will, and blue is, I think, quark or maybe gluon, which has a different structure. So you want to distinguish those based on some kind of algorithms. So what we have been doing in physics since ever is you think with your physics knowledge, what could be a good discriminating observable between those two processes? And you use that to kind of distinguish between one and the other. So for example, for the B quark jets, where the tracks start not from the start, but they start from the middle, you can do the extrapolation. You can measure what's the distance of the extrapolation from the starting point. And this is the so-called impact parameter or D0 variable. And you see that in simulation, this D0 has a different distribution for B jets, which are here in red, and light jets. So this is, let's say, background here in black. So the background is kind of very peaked, and the B jet or the signal distribution is much wider. So you can say that for a jet that has a large impact parameter, on average, it's more likely to be a B jet than a light jet. But in the real world, things are always complicated. Like the signal is never, you cannot completely, pick out only the signal and leave only the background, right? You always have some kind of trade-off between precision and recall, as you may have learned in the course. So basically, you have always this irreducible background. You can never totally get rid of it. And also, you kind of need to then calibrate anyway this method on real data. So you're not really benefiting from using a single variable. So what you really want to do is take many variables and combine them together into something that is more powerful than each of those separately. So then we come to machine learning finally. And basically, the way I see it in the context of high energy physics is that basically machine learning is fitting nonlinear models on large data set with a well-defined target. So it's really fitting. Let's not, let's throw away the image of the talking robot for the moment. It's really basically complicated fitting. And what do you need to do a fit? First, you need a data set. So either a simulated data set or a real data set. But basically, you need lots of examples of what it is you want to do. And in high energy physics, we have had recently good practice that we generate open data sets. We put them online for everybody to experiment with. So for example, there is a challenge for this tracking problem. Exactly like people made up some kind of simplified example for the tracking. You have your hundreds of thousands of, little trajectory points for each collision, and different people can try to reconstruct this or come up with best algorithms. And several years ago, there was this so-called Higgs machine learning challenge, which was for a different kind of classification problem to essentially identify events where there was a Higgs from those where there wasn't a Higgs. So something that we really use in real life, essentially. So there are lots of different other examples of data sets like this that are now also publicly usable for this machine learning problems. Then you need a loss function, right? Something to optimize. So that's really important. If you cannot define what it is you want to get out, there is no way you can ask a fitting function to give that to you. So here I have an example for this classification loss, where essentially you can tune what you ask your classification to give. You can give bigger or higher or bigger or lower weight to, easy to classify examples, for example, and you can really change what is the outcome of the optimization. Then we have different types of models. Okay, our favorite, of course, artificial neural networks. But this is just one class of models. You have an infinite variety of those. And finally, you have the optimizers. Essentially, you want to optimize the model on a large data set with respect to this loss. And this is not a trivial problem. So there is a lot of research ongoing as well in the field of machine learning. What's the most optimal way to optimize, essentially? So here's a little schematic of doing different kinds of gradient descent, stochastic mini batch, and so on. So this is also a sort of, you need basically all of these components to make a successful machine learning project. So a few examples in more concrete details from the high energy physics world. So here we have classification, and specifically for these B jets, so jets that come from the B quark. And as I mentioned, what we want to do is effectively combine individual observables in some non-linear way to classify examples. And in the end, we set some kind of a decision boundary in this classifier. So just to give kind of, probably you've seen this type of an image already here before in the course, but suppose you have just two observables, X and Y, or X1 and X2, and you have two classes, blue and green. So a linear decision would just put like a straight line between those two classes using some kind of optimization, and a non-linear classifier would put some kind of a more complex decision boundary. And you can never totally reduce the background to zero. You always have some kind of trade-off between, what is the precision and recall. So in particle physics, we have been doing this for many years for B jet tagging specifically. And here is a list of variables from one of our papers of all the inputs that go into a modern B quark identification algorithm. So I'm not going to list them out here, but you see there's something like 20 different features. So they are all related to like the jet shape and where are the particles in the jet essentially. And then in the end, we end up with this kind of a distribution where on the horizontal axis, we have the output from the classification. So something that's between 0 and 1 and higher for our signal process. Our signal process here is the red distribution, it's the B jets. And our backgrounds are coming from other particles. So in technical terms, it's C and UDSG, so different types of jets. And what we see here is indeed that the red is kind of peaking to the right and the other ones are peaking to the left. And we compare, so we know in simulation what was what. So that's why we can make this plot like this, right? We know in the supervised case which jets were coming from where. And then we can compare this total distribution with actual real data, so shown here in the black dots. And we see, a pretty good but not perfect agreement between the combined simulated distribution and the real data distribution. And then in the end, this difference in this data and simulation becomes a kind of systematic uncertainty. So we always optimize on simulation, and then we cross-check on real data, and whatever is the difference becomes a kind of uncertainty. So the game becomes both to make the performance better, so essentially to distinguish better between the two classes, and also reduce the difference in data and Monte Carlo, or data and simulation to have lower uncertainties. Then a different kind of example from regression. So regression is you don't predict a single class, but you instead predict some kind of a continuous output. So shown as an example here, you have some kind of input, you have some kind of output, and you have data points which model this relationship. You want to put some kind of a non-linear relation between those two. So we have this very interesting process in high energy physics where the Higgs boson is produced and decays to two of these B quarks. So, and then these B quarks make these B jets that I already talked about. And then you may want to make like a mass plot for those B quarks, essentially to check if the resonance was there or not. But the problem is that there is energy losses in the detector, so the energy of the B quarks is not perfectly measured. So if you were to just make the plot based on the naive measurement, you would get something like the red line here, which is not at the correct place essentially. So the energy is off, it's mismeasured. So then we have this so-called B jet energy regression algorithms, which take as an input a lot of different variables about the jets again. So here I list just to show, how many there are. It's like, I think order 50 or so for each jet. You make a regression because in simulation, you know what was supposed to be the energy. And then you apply this on real data and you check that actually the energy matches better with what you expect. And this is, a sort of a really important method for us to actually get accurate measurements from the experiment. And I would say at any given time in the LHC analysis, you're using something like 10 to 50 different machine learning models at the same time. Like you're not always changing all of them yourself, but at some point somewhere they are running and giving you some results. So that it's always like a chain of different methods feeding into each other. So then some other things that people are looking into but not really using in production so far is, for example, semi-supervised methods where you may have, for example, just a few labeled examples from simulation, and then you have a bunch of unlabeled data, and then you can use those few labeled examples to kind of do some kind of propagation of labels essentially. So what people have done is you remember this problem of distinguishing jets of different type from each other, quarks and gluon jets, for example. So this definition of quark and gluon jet is something we kind of put in our simulation. And it's not always so clear how to make actually that definition. So then what people have done is, what if you could just look in real data and see if we observe like two classes essentially there, and do they correspond to what we actually would put in simulation? And they do this using the semi-supervised methods, and they actually find a pretty good match between our definition of quark and gluon jets and sort of topics that they find actually in real data. So, okay, then going a bit more into the types of models we use. We all love neural networks. They, are very sophisticated, give great results. So what's the main idea, right? It's that they are non-linear, multivariate models with a lot of over-parameterization by design or by construction. So we might easily have models with 100 million parameters, for example, and we optimize them on real data. So you have many inputs and you have many outputs. And just to kind of stress on this question of over-parameterization a bit, here is a plot of popular machine learning models in, let's say, more the AI world. So, for example, GPT-3, which is kind of the latest text recognition model you see up here. And vertical axis is the number of parameters in logarithmic scale. Horizontal axis is the year. So you see it's kind of going really up each year. So now we're something like, what is it, 100 billion, something like this. It's really, huge number of parameters in modern day models. In high energy physics, we are still somewhere around this low end here, but I see this also increasing for us. So then you want to optimize these highly over-parameterized models on large data sets, and you may have learned about this already. So basically, you do a kind of gradient descent over the data set. You try to find some kind of optimum for this function. And if you were to just do it on the whole data set at once, so suppose your data set is 100 million data points, then you would kind of have to do 100 million parameters, 100 million points at the same time, minimize. This is crazy. This is not going to work. So then what people do is these mini batching algorithms where you essentially stochastically pick subsets of the data. You do a minimization of the parameters at each step. And this actually turns out works even better than looking at the whole data set at once, because this stochasticity kind of introduces a bit more regularization into the learning as well. So in real life, these loss surfaces in the minimization may look more something like this, where you don't have like a smooth single minimum, but you have just infinitely many saddle points essentially. So the question is to numerically choose something that's good enough.
How large is the mini batch?
So it really depends on the problem. In our cases, if you're doing event classification, you might use hundreds, thousands of events at a time. For a certain other type of model that I'm going to talk about later, which looks at the whole event and tries to reconstruct everything at once, maybe just 5 events at a time. It also depends on your hardware that you have available. Okay. Yeah. Any other questions or points that you would like me to expand upon a little bit more so far? So, okay, then, of course, what that we have to avoid in machine learning is overfitting, right? Is that you have your data points, you have your model with 100 million parameters. You want to be sure that when you fit that model, that you don't fit the data set exactly, that you don't fit each data point. So this would be shown visually in this image here, where you have 2 classes, and your model basically exactly reproduces the line around each data set. And this is not optimal, because if you take another data set from the same distribution, it's not going to work well, right? So you want to apply some kind of regularization or smoothing to distinguish actually in a more robust way between those data sets. So typically, the way you do this is you divide your data set up into different subsets. You do some kind of train and test split. You train on the training data set, and you observe how you're doing on the validation data set. And you stop the training once you see that you're starting to overtrain on the validation. So this we do exactly in the same way in high energy physics. We really just have to be mindful and careful of this, and otherwise we're gonna develop methods that work really well in our own computer, but will never work in real life. So then you may have heard about different types of neural network models. So we start from our favorite classic feed-forward networks, so the usual multi-layer perceptron that I believe was invented something like 30, 40 years ago already. And this works really well for problems where you can describe your data point essentially in like a feature vector of maybe up to 100 or so features. And if you have no particular relation between those features. So this could be just a classification of collision events in our case. And then, a lot of advances were made in image recognition by convolutional neural networks, which work on 2-dimensional or maybe even 3-dimensional images. And they kind of encode a little bit more about the symmetry of the problem into the model. This seems to work out a lot better. and we also investigated those in high energy physics in the past years. Then there were at some point recurrent neural networks, or these long short-term memory models, which were fairly popular for text-based problems, or essentially where you have a sequence. So again, we investigated this in high energy physics. But what we sort of have arrived at currently in our field is graph neural networks, where essentially the input is a set of points or a graph even, so a set with some kind of edges or relations between those, and operating on this then. And as far as I understand, current state of the art in most of modern machine learning is essentially transformers, which works also on ordered sets, so just transforming sets to sets. And we haven't really looked into this that much in high energy physics so far, but yeah, these are the types of models that are kind of giving the best results at the moment. So to explain a little bit more how we would use, for example, convolutional neural networks in images on our particle physics problems. So if you make these jets, then these jets, they produce lots of particles, and these particles leave images in different parts of the detector. So you can have like this kind of energy deposit image essentially for each jet. So each jet makes a different image like this. And then if you average over many jets of different types, you get like this kind of heat maps where on the top you have the average image from something like 100,000 jets made from a W particle. And on the bottom you have the average image from a different kind of jet. And they look fairly similar, but not exactly the same, right? There is some difference in the radiation pattern. And the idea is then that you essentially train on this collections of images, and you basically try to exploit everything that was done in CNNs in the field of machine learning. You try to exploit this on our particle physics problem. And this was, as far as I know, one of the first use cases of actually deep learning, modern deep learning in particle physics, like something like 5 years ago. So converting jets into images and trying CNNs on those. And this got people really excited because this seemed to really sort of take the performance to a next level. So the idea is with the CNNs is that you essentially encode the symmetries about the problem into the model. So what kind of symmetries does an image have? Basically, if you would look for a certain pattern in an image, it may not matter exactly where is the pattern on the image. So you have translational invariance. And this you can encode by making the model work on essentially convolutions of the image. So you do like little patchwise convolutions, and this ends up being like a filter that you can transform over the image. So, this is a certain kind of symmetry that may exist for real life images. Who knows if it exists or not for images in particle physics?
The filters that you use for the future extraction from the images are like somehow similar to the filters that are used in the classical images.
So we don't think
with 1 - 1 and so
yeah, basically, exactly.
Totally
the idea was at that stage that we just take the best network structures from machine learning and we try them on our jet images. So we didn't invent any particular additional new filters, as far as I know, at least. Because anyway, the network can adjust the parameters and sort of learn best reconstructions or best representations of what you want to filter. Some people have tried to encode a bit more about the physics into those images, but it gets difficult because physics is not an image in the end. Like you already have to make a lot of assumptions when you put your jet into the image. And at that point, you may not anymore have ways to, put like physics knowledge into the convolution. So then we come to the graph neural networks essentially. So we are using these CNNs, for example, for identifying tau particles. So tau is like a heavier cousin of the electron, which can decay in many different ways. So here it's shown like several different decay modes of the tau, which leave this deposits in different parts of the detector. So again, you kind of just grid up the detector into a sort of grid. You measure the energies in each grid cell. You train a CNN on this. And it turns out that the CNN works a lot better than whatever we had before, which was essentially some kind of boosted decision tree. So here on this plot, it's the typical like signal versus background selection plot. So horizontal axis, we have how much signal are we selecting from 0 to 1. So you want to be as close to 1 as possible. And on the vertical axis is how much background are you selecting. So you want to be low on this axis. And we see the previous models are here in red and green, and the new model is here in blue. So it's something like, I don't know, like 5 times better than the previous models. So this was a, obviously a really great result for physics, because if you can identify some particle 5 times better than before, this can really change the game for physics analysis. But then we come to a bit of a computing challenge. So here on this plot, I have the evolution of our computing needs and capabilities in the experiment as a whole over the years. So this is extrapolating into the future. And in the gray shaded area, we have what's our budget for computing, how many thousands of CPU hours we have, because it's really a huge computing problem that we have to solve. So we are fixed by the computing budget. And then in the blue lines, we have how much computing do we need according to our predictions when we start the data taking for the next phases of the experiment. And you see obviously here a big discrepancy between what we need and what we have, something like 4 or 5 times. So the problem is we have to fight really for every CPU cycle or GPU cycle and every kilobyte of memory. So if you have your jet image and most of the image is empty, and you have to do like 1,000 by 1,000 grid calculations, it just gets too crazy. It's not computationally efficient. So we have to find new models that would be much more efficient computationally for these types of problems. So then we come to graph neural networks. And basically the idea is that you don't put your data points into a grid, which is kind of a bit artificial perhaps. You build relations between the data points as needed. So suppose you have your event. So this is one picture of an event. Event can contain many jets. So each of these little clusters here is one jet. And in each jet you have many constituents. So many like little data points or particles in the jet. So then if you look at one jet, this could consist of many constituents, and each of those constituents has some feature vector associated with it. So then you can arrange them as kind of just a set of vectors, and you can make a feature matrix from this without imposing any particular ordering on them or without kind of embedding them in a 2-dimensional image. And then you can turn this set into a graph if you build some kind of edges or relations between those nodes. And those edges or relations you can represent as fine in as fine detail as you want. So if you have few of them, you can just give a list of the edge indices. If you have many of them, you can represent them with this adjacency matrix, which may be sparse, for example. So you really have a lot of flexibility to encode what are the relations between the objects that you have. And then you can run basically a neural network on this data. So you have your input as a graph, and then the graph consists of nodes, edges. You can embed the nodes and edges into some kind of feature space.
In the previous slide, if the arrows are double direction, then that matrix becomes symmetrical.
Yes, yes.
So that is like the row is the number from which is starting, and
right, right.
Where is the
yeah, so this is a kind of example of a directed graph. This depends on the problem, what you're trying to model, if it's directed, undirected, if you have self loops or not, all this kind of things. So for example, here, the diagonal is 0 by construction because we don't have any node connections to themselves, but you can have all kinds of different things. Yeah, correct. So yeah, as I mentioned, you can start to run neural networks then on those graphs without embedding those graphs into some kind of other grid. So it's really just operating directly on the data. So the idea is you can embed nodes and edges, and then you can transform the embeddings of the whole graph with something that's taking into account the connections. So essentially you sum over the incoming and outgoing nodes, for example. That really depends on the type of network you're doing on the graph, but essentially you're transforming the graph. And then you can have different types of predictions for the graph. For example, node level predictions, where you would decode the hidden dimension of every node into some kind of prediction, or you can have graph level predictions, like if you want just a single number for the whole graph. You can have age level predictions, different kinds of things. And obviously in the end, you're still operating on big matrices, as you usually do in neural networks, machine learning. So you kind of have to write this all up in TensorFlow so that the operations on the graph end up being sort of matrix operations. So then we come to a bit the question of how do we actually construct these graphs for practical problems. So you may have your data points, but the question is, what are the relations between the data points, like in this chat, for example? You can have different types of relations. So the simplest you can do is you just assume or make up relations between all the different data points. So you have like an all-to-all graph. This is kind of the most generic, but also encodes the least knowledge on your side. And the problem with the all-to-all approach is that if you have many data points, like 1,000, then you will need 1,000,000 edges. And that quickly again runs into computational problems. So this works well for cases where each example has a few data points, like maybe 100, but not much beyond that. The other thing you can do is you can predefine some neighborhood in the feature space and build a graph in this predefined neighborhood using something like k-nearest neighbors, for example. So this is, of course, computationally more efficient than the all-to-all approach. Would scale also to larger graphs. But then the question is, like, this becomes essentially like a hyperparameter. You know, what sort of neighborhood do you want to define? The other option you can have is you can essentially embed the features into some learned feature space and then build some kind of neighborhood in that learned feature space. So then your graph essentially becomes dynamic in some sense. And people have been looking into how we can encode our high energy physics data as graphs for different kinds of problems. So for example, this particle tracking, where we have to make the trajectories. So we could say that each of the hits in the detector is like a node in the graph, and then the track would be the correct track would be this edge, essentially. So the set of edges that connect, and you want certain properties from the graph. You want things to be disjoint and so on and so forth. For this calorimeter clustering, where you have hits of different granularity in different layers, like this, you may connect, for example, nearby hits in nearby layers, and you can run some kind of inference on this cluster then. If you have this jet identification, so here we have an event with 3 jets. So this red jet, green jet, blue jet, each of those has a different number of constituents. You can just make an all-to-all graph between everything and run a jet identification algorithm on those. Or if you want to do event identification with different objects in the event, you can again do kind of all-to-all structure between the objects. So in a nutshell, for this graph networks, graph programs, you have different things you can do. You can do a node level prediction. And in the physics case, we have so-called particle flow reconstruction, which essentially aims to reconstruct all the particles in the event in a sort of node level prediction sense. You could do something like subgraph or community detection. So this would be this clustering of detector hits. Or you could do edge level problems, edge classification. This would be, for example, this track reconstruction. Or you can do graph level.
Yes, meeting closed, but we got disconnected for a moment.
Okay, well, I guess we're back now.
Yeah, all the participants are there.
Mm-hmm. So yeah, for all this tracking, yeah, we have just an image after the whole thing happened. We don't have the evolution like a movie. Oops. So this is a snapshot from this living review of graph problems in particle physics or machine learning in particle physics. And here's the graph section. You can see a lot of papers in the last few years have been already published on this topic. So just to give a snapshot that it's really an active field now. And I wanted to talk in a little bit more detail about one paper. So this efficient particle reconstruction, which is also something that I co-authored with people from Caltech and CERN. So I have a bit more knowledge into what's going on in that model. But before we go into this, okay, we are now at 1 hour. And any questions so far that came up?
Sorry, seems to me
Doesn't seem to be the case. So I'll do a little bit of a deep dive, maybe 15 minutes or so into this particular model. And then we can do sort of, summary and roundup. So this particle flow reconstruction, the idea is you observe all the different clusters, tracks, whatever in the event, and you want to reconstruct all the different particles that made those together with the overlaps and everything. So it's kind of like you look at the whole collision as a whole, and you want the most optimal reconstruction in terms of particles. So the particles we're leaving the signals as on this picture here. And there is a standard algorithm that's running that's not based on machine learning. That's kind of iterative and based on heuristics. So the idea is more or less that you take the calorimeter clusters, you take the tracks, you link the tracks and the calorimeter clusters in some proximity. Then you start to reconstruct charge particles based on the stuff that's linked there. You remove those detector hits, and then you do a next iteration and so on and so forth. So this is encoded in this image here. You can see it has a lot of boxes, and this is a simplified cartoon, what's happening. So the algorithm ends up being really, really complicated. There's a lot of rule-based logic there, which basically none of it has like a particularly strong physics motivation. It's just something that works in practice and that has a good enough response. So the question is, can we do better using machine learning? And here is a snapshot of the main paper of this main algorithm that we're using in our experiment, particle flow reconstruction, blah, 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 blah. It's published in 2017. It has something like 1,000 citations. So it's really the main workhorse of our experiment, if you will. It's the algorithm that does one of the most complicated things. So we want to sort of augment this with machine learning. So what can we do? We can generate simulated events where we have the sets of particles that we want to reconstruct and where we have the signals that those particles would leave. So here's one event. And we have, for example, the tracks in the gray lines here. We have the calorimeter clusters in the different parts of the detector in the blue and orange dots. And we have the particles that we want to reconstruct in the red dots here. So each particle is just a dot, but actually each particle also has like a classification ID, like was it electron, muon, whatever, has energy, has different properties like this. So it's really like a combined classification and regression problem. And then basically in a nutshell, we have proposed a graph neural network algorithm that can look at the whole set of observed hits and reconstruct the whole set of truth particles. And we can compare this to the existing algorithm. So let's look at this plot here, where we have on the horizontal axis the true number of particles per event, and on the vertical axis the reconstructed number of particles. And the baseline algorithm, this rule-based logic, is the blue dots. And you see it's like pretty good. It's representing or reconstructing pretty well what's in the event. And the machine learned algorithm that does this whole thing with essentially a graph neural network is the orange dots. It's similar, maybe a little better. So how does this work? So we start with the event as an input set. So as I described, basically each hit in the detector is just like a point in the set. Then we need to build a graph in the set. So we do this using some kind of dynamic nearest neighbor, essentially in a feature space. So we end up with the event as a graph. So we have our point set, then we have an adjacency matrix. And just to give some context, each set contains something like 5,000 to 10,000 particles. So we cannot do an all-to-all. This would be much too memory hungry, essentially, if you want to train this in practice. Then we run some graph neural network on this graph. For example, graph convolution. We transform each node into some kind of hidden representation, and then we essentially decode each node with some kind of feed-forward network into a particle candidate. And then we compare this with a loss function, which is essentially element-wise. So each particle is compared to one other particle. And there is a classification component there to predict what was the type of particle, and the regression component to predict the energy of the particle. So essentially, this model has dynamic graph building, and the loss is based on an element-wise set-to-set loss. And the idea is, okay, it's nice to write down on paper, but if you want to actually train this on a real data set, you need to make sure that you can write this in a differentiable way, firstly, like with TensorFlow, essentially, and that you can compute this on a real hardware that you can access, that you don't need like a GPU that has 100 gigabytes of RAM or something crazy like this, although this is actually not that crazy anymore these days, but you can actually compute this on real hardware. So we did that. This was kind of a little snapshot of our model. So we start with the event in a 3-dimensional matrix. So batches of events In each event, you have a number of elements, something like several thousand. Each element has a number of features. Then the model has kind of two legs, one leg for classification, one leg for regression. And each leg consists of feed-forward layers and these graph layers, which do kind of information propagation from elements to elements. So in the end, we encode all of these nodes, and then we do a decoding of those nodes with classification and regression feed-forward networks, and we predict a set of particle candidates. So we have here these so-called combined graph layers, which are essentially layers that take a set as an input and give a set as an output. And internally, they build a graph and do message passing between the nodes in the graph. And this combined graph layer was implemented in TensorFlow. So here is one of these layers. The idea is that if you have like order 10,000 or so points, you cannot do, as I mentioned, an all-to-all matrix, because that would be 100 million points, I think, right? It's way too much to put into a batch training. So what you need to do is kind of blockwise sparse connections between those elements. So we do a kind of locality sensitive hashing to divide local regions of the set into like little all-to-all connectable areas. We build a matrix in each of those areas, and then we connect this all up. So this is basically based on approaches that people are doing for transformers, where you want to run transformers on huge sequences. Like if you want to run a transformer on something like 10 to 100,000 elements, it again runs into this quadratic scaling problem. So people are looking into models that can scale better than quadratically on long inputs. So we did here the same. So here you can see, for example, for one event, this sort of how we can split up the event into little local areas that talk to each other. So each color here is a different local area, and each dot is one of the sets, one of the elements in the set for one event. And you see that in the like XY plane where we observe the set, this areas kind of, they make up some kind of topologically connected parts. And of course, this is just two features. In the end, we have something like 20 features for each element. So this connection happens in all the dimensions at the same time. It's not the nearest neighbor in just 2 dimensions. And then in each of those little connected pieces, we basically build dynamically a graph. So here is the adjacency matrix of each of those little graphs. So this is something like 60 by 60, each little square here. And then we have something like 100 or so, little bins where we build a graph. So you see that it's really like a very diverse data set where you dynamically need to build different kinds of relations between the objects. And this all works in TensorFlow. You can train it on a data set. We've done this on an open data set that we put out online. And we have also applied this recently in our experiment. So here you have one event reconstructed with standard particle flow on the left. So each line is one particle essentially. And on the right, it's reconstructed with a machine learned algorithm. So the algorithm just takes as an input all the detector hits and gives us an output set of particles. And this is the first time that I know that we've shown a full and realistic event reconstruction using machine learning in this experiment. So this is something that many people are working towards, and this is now becoming kind of practical and realizable. So we trained this on simulation in the CMS experiment. So we generate something like 40,000 collision events with a lot of particles in each of them. And then we additionally generate sort of fake samples where we put just a single particle of a single type into the simulation, so we can kind of get like a more physical response. So like the idea would be, if you have, say, a self-driving car, you just drive around, you get what does the real world look like. But if you have some very rare cases which you don't have a lot of, you can try to augment your data set by introducing a lot of those rare cases in some, you simulate them essentially. So here we do the same, that we have real physics events, and then we have events where we put just a single particle to get those guys really well. So we make like a big combined data set of all of this. We train this for something like 5 days on 5 GPUs in our cluster, which is actually very close to here where the KBFI building is. And our CERN colleagues also ran a hyperparameter optimization of this model at the Jülich supercomputing center. And in the end, the loss function looks like something like this. So here we train for 200 epochs. We have the training and validation losses. the shaded area is kind of the average or some kind of spread over 10 different trainings. So we see if the model is stable or not. And we see that the loss kind of converges in a nice way. And then we can look at what's the output of the model and compare this with the baseline model. So here we have the particle distributions in, for example, momentum. And we have different types of particles shown here in different colors. And we have the baseline algorithm here with the lines, and our algorithm with the dots. Basically what we see is that the lines and dots pretty much overlap. So the machine learned model predicts to a large extent the same physics response as the baseline algorithm, which is exactly what we asked it to do. And it's not doing it only for the most common particle types, but it's really also doing it for the rare particle types. And then we can see if we then feed those particles into the next steps in the reconstruction, for example, to make those jets, which are done basically by clustering these particles in the detector, then we want the jets from the baseline algorithm and from our algorithm also to look the same. And here we can look at, for example, the momentum of the jets from the baseline algorithm in blue and our algorithm in orange, and we see they overlap really well. So this means that not only can we predict the correct set of particles, but those particles have the correct properties that they can be used by other stages in the reconstruction and give a correct result. And then we can go even further and look at sort of global event level properties. So one of the things we always look at in high energy physics is so-called missing transverse energy. So the idea is if you have an event and lots of particles in the event, the one thing you do know is that if you add up the momenta of the energies in the transverse direction, it should all be zero, because essentially the beam is not moving in the transverse direction. So energy should be conserved, except if you have invisible particles that are not detected by the detector, like neutrinos, for example. So then you add up all the energies in the transverse direction, you see how much is left over. So this leftover energy is like a vector. It's called the missing transverse energy. And it's a really strong signal oftentimes of new physics, because new physics might produce particles which are not detected. So then we want to see that we reconstruct this missing energy also in a proper way using the model, basically just by adding up the energies of all the particles in from our prediction. And here we see in the left for one data set, and we see a pretty good match between our model and the baseline, and on the right for another data set that was never used in training. And actually here we see a difference between our model and the prediction. So the idea is that, okay, you may train on your simulations, and then you apply on a different simulation, and you see how well does the model actually extrapolate to a different set. And here we actually see a problem that this other data set has a slightly different distribution of certain types of particles, which is not expected by the model. So it's not that efficient in reconstructing them. So because we miss a few of those high energy particles, actually this kind of distribution can start to look not that good. So the idea is that, when you do a kind of validation of the model, you really want to check on all kinds of different situations how well you are doing, not only in the same kind of sample where you trained on. So, suppose you're training only on the Tallinn streets, but then you apply it in Puerto Rico, probably it's going to work in a different way because people are different, right? And here as well, physics is different in these different samples. So what we can do to improve this, we can basically generate more data sets from various different physics scenarios, include them in a training, and then we should be able to improve on this.
Just to understand the idea of this missing transverse energy, it sounds very roughly, it's the same approach that did Compton when it was searching for the light.
Yeah.
Somehow.
It's very similar. Very good.
So instead of light, it's neutrinos and
right.
Okay.
Yeah. So all particle physics experiments are basically redoing Compton's experiment with the scattering, just at different energies. So then, as I mentioned, our models also have to be fast and not require ginormous amounts of memory. So we construct our model explicitly to avoid this kind of quadratic scale up. So if you have 1,000 inputs, you don't want 1,000,000 computations on those. You want less than the square of those. So we observe this also in our model by construction. So here we have the runtime in terms of how many signals were there for each event. And you see it's kind of linear. And here we have the memory usage. And this also doesn't increase quadratically. So this is really a good sign for the next, let's say, decade of data taking, that we can train machine learning algorithms that process the whole event without requiring as much resource as a normal algorithm would. So the next steps we want to do with this is actually test this on real data in our experiment and see how well we're doing for reconstructing really real cases, not only simulation. So coming kind of to the end of this presentation, so some lessons that I've learned, over let's say 9 years of this kind of activity is that firstly, really the data set is the whole thing. In the end, the model is a kind of summary of the data set. So if you don't have a data set, you cannot do anything. You need something there. The second thing is that before you do anything complicated, it's good to set up a simple baseline, usually like a simple feed-forward network, and also simple performance metrics that you can understand, like some kind of accuracy, some kind of regression, deviation from the mean, so on. And this performance metrics should not depend on the model that you have, in the sense that you can always measure different models in the same way. The numbers will be different, but you should be able to measure the performance independent of the model. And I think this is really important because sometimes the model and how you measure the model are somehow convoluted together. And obviously, if you're changing something in your whole setup, never change two things at the same time, because then you don't know what gave the effect. So always change one thing at a time. It's really tedious, but that, really does seem to help. And if your model is not yet working, it's good to visualize sometimes a few predictions and then see visually sort of what's going wrong. What are the easy ones? What are the hard ones? And this can give you a big intuition also into the data set, like what you might miss still in the data set. And the second thing that I found really useful for this past project was that it's good to visualize how the learning does over time. Because if you train for 5 days, maybe in the first day you learn like some really simple cases and those work out well. But if it still keeps improving, what are the parts of the learning that still keep improving? So it might be the very rare, unusual types of signal. So if you visualize how you are doing over time in terms of performance, this can really help to understand like what is the model focusing on right now. And yeah, coming back to this simple baseline, generally like introduce this fancy stuff one step at a time, and not before the simple stuff is you understand a bit how it works and how to measure it. For example, batch normalization, easy way to shoot yourself in the foot. If you like are not particularly careful about how you're leaking test and training data sets and so on. So this kind of things you really have to, I think, do one thing at a time and carefully. And the general approach that we're not always successful with, but seems to be really helpful, is that use existing models where possible. Don't try to invent your new hot model if you can use something that already exists out there. Also because of the infrastructure that might be already set up for training something like a transformer from Hugging Face versus making it up on your own. And of course, as we know, machine learning can only answer questions that you can pose, and you can pose in a quantitative way. So it's not going to find patterns for you in the data if you don't know what is the pattern, how to define it, how to measure it, and so on. So it can really only answer well-defined questions. And I think that's really a helpful heuristic, because it helps to boil down the problem into what is it that you really want to get out. And of course, as we also know, all models are wrong by construction, because if you had a model for the real world, it would be the real world. But some models can be useful under certain conditions. So, none of the models are correct, basically. So coming to my summary, the last slide, basically in fundamental physics, high energy physics, we have a really interesting use case for machine learning, because we have a fairly good predictive model, which we can use to make simulations, which we can then use to train models, and also answer questions about how well those models work. And we have also a huge data set from our experiment, and really complicated problems that we want to address with those data sets, like what is the origin of mass? So this needs like a huge signal to background rejection. So this is a fairly unique situation that we have. We are not limited by the data as much as maybe, a different type of problem where you might have to go out in the field and collect the data. So the LHC ends up being a very rich playground for machine learning methods. So at any given time in our experiment, we have something like 100 different models running in production, which you might be using all of them if you're doing some analysis without really thinking about it even. And as far as I see it, at least, machine learning is basically fitting distributions on data sets. So it's not developing artificial intelligence or something, you know, bombastic like that, it's really fitting. And obviously you can do fitting in different ways. And if you can find some way to encode your knowledge about the underlying processes in the models, and usually this ends up being through symmetries, you can really improve the performance of the models. So from this we come, you know, to the graph neural networks, for example, where you have really a lot of freedom to encode what you know about the process. Okay, this was my last slide. Questions? Something you want to discuss?
Would you like to turn on your volume if someone asks?
Oh, I think there's going to be an echo then. The volume is on.
Oh, okay.
Yeah, so I guess you can speak up also from the meeting room or the Zoom room.
Nobody from, like the last point here, like basically means that if we are able to make like a good hypothesis that we are in some way sure that it's correct, then this hypothesis is like cutting out like a lot of computation from the model.
Right, right. This ends up being true in many cases, not always, but yeah.
And this is going to another question that was in the previous slides, in the things that you learned. The third point was regarding like testing your hypothesis. Like at certain point, I lost like the point of the coupling the model.
Okay.
And how to.
Yeah, I see what you mean. So suppose you have a question: does a CNN or a graph neural network work better on my problem? You know, convolutional net or graph net? Then you should be able to find a way to measure this independently of what was the model itself. Like you have an accuracy that you can define, and you can measure whatever the model was, like just with respect to the predictions. So sometimes it can be that you start to think only about your model, like, okay, I have a cool graph neural network. So the way I measure the performance of this network must be somehow tied to the structure of that network. But actually it's only tied to, you know, what are the predictions and what are the ground truths. Sometimes it's very easy, like in classification, but in other cases, it can be less easy. So for example, this tracking problem, let me see if I can find the picture. So this problem here, zoom in a bit. So you see the way it's formulated here is your nodes are these track hits, and the correct tracks would be kind of like the lines in the edges between the nodes. Now it's not like this on this image exactly, but then the question is the way you measure how well you reconstructed the tracks, is it connected to the structure of the model or not? And my claim is you should find ways to state the accuracy or whatever other metric you have independently of the structure of the model. So basically, like you count how many tracks did you reconstruct correctly and how many tracks did you reconstruct incorrectly. And GraphNet or CNN or feed-forward network or Kalman filter or whatever should be able to give you some kind of a number for that. Yep.
Could I ask about deployment? How many of those models are going to deploy real time? Are there any? Or
very good question. That's a whole topic in itself. At any time we are running something like okay, really real time, like 40 megahertz, maybe just a few models, because they have to run directly on a chip. Like they have to be compiled into hardware essentially, like FPGAs. But then for offline processing, where we have to do the reprocessing many times over, we have a bit more freedom. There we have hundreds of models running in a production setup essentially. So it's not real time as such, but it's still under very tight time constraints. Like this graph with the computational scaling, we have to really be mindful of that. So actually one of the things I'm doing for the experiment is I'm coordinating all the software that goes into the reconstruction. So people from different groups are developing models that have to be kind of all run in the production software without blowing up our budget. So yeah, this is a very big challenge. So just recently, like last week, muon identification people developed a nice random forest model for muons that takes as much memory as all the other models combined. So now we have to find a way to like bring them down to the earth and make sure that we can all run in the production system in a good budget, because we have so much simulation and so much data that we have to run the computation on a global scale, essentially. So we have a own cloud that we have built that's running in different universities all over the world. Here as well in Tallinn, we have a big center, and there is, in different, like 100 different similar clusters of thousands of computers. So you have to make all this like work well.
May I ask like which language do you use for doing all?
Very good question. So the model training is usually just Python, because I mean you just schedule TensorFlow, schedule PyTorch stuff. Then you have to export the model somehow. And if you want to run in production, usually you have to kind of run it in a C++ environment in the end. So TensorFlow is pretty easy. It has a C++ interface, and TensorFlow models are static graphs, which can easily be run on a well-defined computing budget. We also export to Onyx, which is a library from Microsoft, which is supposed to be a common inference library for different kinds of models. And then we have upcoming developments like how to run PyTorch in production, which is really complicated apparently, because PyTorch is so dynamic so that you cannot really properly integrate it with something where you have tight time constraints and a C++ program. So then people are doing something called remote execution, where you have like sort of, let's say, microservices idea of inference, that you have a server where you have the model, and you have another server where you have the production software. The production software makes callouts to the model server, and the model server returns the result, and you have this kind of like client-server architecture. But yeah, Python and C++ are one of the main languages, I would say.
So, like, sorry, just if I got it correctly, like you make the, let's say, like the high-level code, the high-level code and the high-level ideas on Python, and then when it's going to like big computation, it's going like low-level like operations on C++.
Right. But I mean, yeah. So basically, for inference, we have a specific environment simply, and then you have to export the model to something that can run in that environment. Like if you want to run real time, for example, you have to even export your model to a chip layout, pretty much. Like you have to compile it to an FPGA code, effectively. But if you do training, you still basically write TensorFlow in Python, pretty much. At least as far as I know in our cases. So we're not doing like Tesla, where they're like rewriting their network from scratch in C++ for inference or something like this. We still export essentially. So we try to be a consumer rather than producer of softwares.
What's the size of the, I mean, if there's this term like average data set?
Yeah, good question. So this data set for the model I talked about for this particle reconstruction, this was something like tens of thousands of events. Each event consists of like 5,000 particles. So, let's say 10,000 by 5,000 data points, if you will, or feature vectors. So it ends up being like maybe 10, 20 gigabytes, something like this. Not very large in some sense. For this event identification, BJT identification, I think it's order of 100 million examples. Like each example is one jet or one event. And, size also ends up being like somewhere around 100 gigabytes or so, because that's in the end what you can conveniently train on if you're a like reasonable person without access to crazy hardware. So for the most part, the models we are training are still trained on fairly small devices, like not like GPT-3, which is trained for, I don't know, 3 weeks on 100 TPUs or something like this. We don't have this kind of resource. So, we train maybe a few days on a few GPUs at this stage.
Thanks.
Any other questions?
Some sources for us to learn deep learning.
Deep learning. Okay, so I have mostly talked so far about deep learning in high energy physics. So the problem set is a bit more focused. So I really liked these lectures that I linked here. So this is a physicist talking about, like, you know, deep learning problems as they relate to physics. General deep learning resources, I couldn't say I have one favorite or so. I mean, these days there are so many different resources that you kind of have to choose. Do I want MIT lecture or Stanford lecture? So you have to be picky in that sense. I don't know, general resource, but I would say a good way to do a project is to come up with a concrete thing you want to do. So you have a data set and you have a problem that you want to do on the data set, and then you can do a real life, you can try actually a real thing. Because yeah, as you also I think said in an email, often you see these nice pictures of like classification in 2 axes. You see this picture, and this is like looking very trivial, but then you want to do a real thing and you kind of are not sure where to start. So I think, for this, it's good if you have like a list of projects to choose from, for example.
Let's expand the last question a bit. If any of the students from this course would like to end up working on similar problems or CERN, what would be the path?
Very good question. So CERN has a summer school that you can apply to. Happens every year in the summer. I think application period is about now, and if you go online, you can find information about it. There are also ways to get engaged through research groups. So, for example, our research group in Tallinn, we are working on these types of problems. As I explained, we have master students, PhD students, so on. What else? There are these challenges. So, as I mentioned, these open data sets from the CERN problems, usually they end up on these challenge websites like Kaggle or whatever. And you can kind of get some example code, example data set there and participate in some, more global effort. So right now there is an ongoing challenge for unsupervised learning in particle physics with a kind of interesting data set. What other ways?
Sorry, you mentioned master students in the sense that it's possible to make the thesis.
Yes. So like one thesis topic that I could personally think of would be to continue this model. So we have now made like a publication and some first application in the experiment, but to essentially continue this works. And also we are looking into ways of applying now similar types of models, not on particle physics data, but on astrophysics data. So Gaia satellite measuring 1 billion stars and then deriving some information from this. So a number of things ongoing. But yeah, I guess if you are like here in Estonia, the main question is to get connected to some bigger community in the wider world who is doing this kind of work. So I recommend to look into summer schools, maybe not only the CERN summer school, but other summer schools or summer internships where you can get some research experience.
Sorry, last question. May I ask you where did you study?
I did a bachelor master in Estonia, in Tartu. Then I did PhD in Zurich at ETH. And then I did postdoc at Caltech, not Taltech, but Caltech. So yeah. And then last year I came back to Estonia.
Does anyone from behind the screens would like to ask something? Would anyone say that we should count to 6 before concluding? If no one would like. Okay, thank you, and thank you, Joosep.
You're welcome. Thanks for the invitation. I'll stop sharing.